We're going to take this final opportunity. We're going to take this final opportunity to clue you into a fact. The math with the calculator is much easier sometimes than the math with the CAD, but especially when you head into 3D. But we're going to use an example here of a truss. Right now we're going to apply a force. It's an odd truss, and I'm going to go ahead and put a couple more members on here. Line from the midpoint between 2 points up, line from the mid of that to the mid of that. I'm going to put a line here from the end of that to the mid. As you start thinking about how trusses work, etc., you can start to realize that at any 1, 2, 3 points you may or may not have any forces in a particular member. So for instance, this one here, unless there's a force applied right here, there will be no force in this member. It's a zero force member. Remember how you basically go through, and I'm going to add one more line here from the end point here to the end point there. Remembering how you go through and you add, basically you count the number of nodes, count the number of members, and do some math to determine whether it is statically determinate is the word. So I'm just extending, I'm just basically making sure each of my members there extend. Right, and what I'm going to do right now is just apply a force line down at the bottom here, and we're going to start calculating forces around, but mostly we're just going to look at the calculations in the calculator. We'll re-look at this of how we solve for the reaction there. So you solve for the reactions first. I'm going to go ahead and put a force concentrated line from the end of this. I'm going to decide that I'm going to make my forces 1 to 10. Hit F8, so I'm going to do, because I got the recorder, I'm going to go at 1, we'll make it 1 to 100, at 1 angle 270. So each of my forces basically now are going to be 100 per 1. UCS, the end point there, enter to accept. If I list this, I have a distance, or an x of 3.46. When I list this, it is 20. So the calculation is going to be 20. For the reaction there is going to be 20 minus 3.4641. So divided by 20. Remember the lever rule. 20, turn this on, 20 minus 3.641 equals, divided by 20 equals, times the 100, 81.8. So I can go ahead and draw a line now here on the right layer, force reaction, a line from the end point here at 0.82, if I would, 90 degrees. UCS icon off. So what we have now, and in the end we would have over on this side, we won't do the calculations. I want to point out that we're not using this right now to solve for reactions. I'm just giving an example of how quickly reactions are supposed to be solved. We can do the same thing over there. We can do 3.641 divided by 20 times 100, and we got it more or less the 0.18. I'll go ahead and put the 0.18 from the end point there, line from the end point at 0.18, angle 90. Now, so there are my forces. Remember, forces are 1 to 100, but I want to point out now essentially how fast the calculator can work as opposed to doing it Well, in all reality, it's probably faster in the end to do this for a concurrent force if you know how to graph. I'm going to copy that force over here. Remember my 0 point was there. I'm going to pick a direction home. So I'm going to copy that force here from the endpoint there to the endpoint there. I've picked a direction home. I've got to get from there to there along the other direction. I'm going to copy this here from the endpoint there to the endpoint there. And then if I'm smart, I just more or less figure out that this is one reaction, this is the other reaction. In other words, that is the force in there, and so I can draft on top line from the endpoint there to the intersection there to the intersection there. And so we see that in this case that the force is 142 pounds in that member. It is tension, and the force in that member compression is 164 pounds. Remember, this here is only 82 pounds. So that's how you can go about, and you can more or less go ahead and pull these things back over on top, do whatever you want to do, but that's how you can do that. Now let's look at how you would do it with a calculator. And the way the calculator works is essentially it's matrices. You're going to go ahead and put the unit vector that describes each of the tensile vectors from here into the calculator, and of course we need to know what that is now, and put the opposite of the externals. In this case, the opposite of 0.81 is minus 0.81. In other words, this is pushing up, so you're going to put a negative 0.81, which of course in this case will be down. You know that the weight is acting down, so we're going to see how we do that in the calculator. It's a 30-degree angle, so it's this straightforward. You can go second list, got to turn it on of course, second open the list, cosine of 30 comma sine of 30, close the list, store it into second list 1. And then I start another list. Cosine of, if you think about that tensile, 0, that is the other member, comma, sine of 0, close parentheses, close lists, store it into second list 2, and then you're going to do the opposite of what the opposite of plus 0.81 is a minus 0.81 in the y, and you're going to do that by doing open list, second, 0 in the x minus, I guess if we do it consistently, 0.81, even though we know it's 1 to 100 scale, second list there, store it into second list 3. Now all you got to do is second matrix, you put them all together by using the basic math function of list to matrices, and it stacks them in columns, not rows. So list to matrices, second list 1, comma, second list 2, comma, second list 3, comma, second matrix, and you're going to put it in your 2 by 3 that you've got hopefully there, close it up, and all you have to do now is second matrix, reverse row echelon format. Remember what that is just solving for systems of equations, reverse row echelon format, second matrix, list D, close your parentheses, and you get a calculation of 162 and 140. Let's check that. Is that what we got? List 142, that's the mathematics, and 164. And so if we look which is more correct, we'll have to chase it down, but they should both be the same. They should both be the same. And they should be the same because we did not kind of lose. Let's check our lists again. Second, list 1. Second, list 2. And again, the difference, I think, is this vector there, list, would be that distance there. So that was where we missed, was then in terms of the reaction force. But seeing that those two things together work out is something to know. Thanks for listening. We'll do it in 3D next.